Jachymski from Warsaw, who will again talk about something that I don't see yet, but he will tell us. It will involve dipoles. That's as much as I can say.
Yes, thank you very much. So good afternoon, everyone. Yeah, it's great that we started with a very elaborate talks of many-body physics between dipoles by Anna Maria and Luis. And then Arthur brought us a little bit back in the complexity. I will reduce the complexity even further because we are all tired and we are waiting for lunch, and tell you about some results that that were obtained mainly by my student Michał Zdzienicki and his older colleague Piotr Kulik and Sakti Kumaran, who are all in my group. And we collaborated on that with Center for Theoretical Physics, which is nearby in Warsaw, with Professor Krzysztof Jachymski. So what is it all about? Well, I can skip already the motivation and how we all like anisotropic and Lagrange interactions. Let's just jump straight to the formulas. So we have a system of magnetic atoms or polar molecules, and we know well that the situation is much more complicated than what I'm showing here. But essentially, they have this dipolar interaction that we are all most interested about. There is also some short-range van der Waals interaction and a lot more terms due to other short-range processes that can happen. And we typically want to put them in a trap. Here I wrote a harmonic trap. But in principle, you can put them in an optical lattice and do all this nice fancy stuff. And basically try to use that as a quantum simulator of something else, like extended Hubbard model or some spin chain system. So the first task is to try to map what is happening microscopically to this macroscopic effective Hamiltonian that we want to describe. And typically this is done using very simple assumptions that I will now try to test and see how they work. So I neglect all the anisotropic van der Waals interactions, all the chemical reactions that can happen. This is complicated enough at this level. And the problem that we get typically in these strongly dipolar and strongly interacting systems, especially if we put them in tweezers, is that with each of these terms you can associate a length scale, and all of these three length scales can easily become comparable to each other. So with neutral atoms like rubidium, you would have typically a separation between the van der Waals length and the trap length scale of orders of magnitude, while here in our confined system, all of them are similar, which means that it's much harder to justify using single mode approximations and pseudopotentials. Yes, so the system that I will focus on is just two of these dipoles put in a strongly anisotropic trap so that it mimics a 1D system, just a tube. But qualitatively, you can think also about optical lattices, and you will have similar problems as I will have here with this system. And putting things in 1D tubes, of course, allows you to do a lot of interesting stuff like simulating Lieb-Liniger models, which, if you add long-range interactions, can become slightly more complicated. Yeah, so what are people typically doing if you want to put dipoles in a quasi-one-dimensional trap? Well, the temperature is very low, so they will just occupy the lowest state of this trap, which is a Gaussian wave function. So let's just project the interaction potential on this lowest mode, and what you get is a beautiful expression involving some error functions, which magically decays with the third power of the distance, just like dipolar interactions, if you use some series expansions. So it's essentially the same with some short-range correction. It has a cusp at short range, but nobody cares about that. So the conclusion from this would be that the dipoles in a trap still interact by 1/r³ interactions, And the crucial parameter here is the relative angle between the dipole orientation, if we are thinking about fixed magnetic dipoles oriented by external field, and the direction of the trap. So if you put dipoles parallel with the trap axis, then you get 0 here, and the interaction is attractive. If you put them perpendicular, then they are repulsive. And if you tune it to like 55 point something degrees, this whole term vanishes, and essentially you should get non-interacting dipoles. So it's very simple. It has just one problem. It doesn't work. And this has been shown even for contact interactions in 1998 by Maxime Olshany, that if you really solve a scattering problem in a harmonic quasi-1D confinement, you get at your effective one-dimensional coupling, which looks like the coefficient that you would get if you just integrate over Gaussian, times a correction, which is not necessarily a small number. It can be infinity if this denominator is 0. And this can really happen because you have access to the three-dimensional scattering length. You can tune it by Feshbach resonances. If you make it of the order of the transverse confinement length, you get a confinement-induced resonance. So all this one-dimensional projection breaks down. And this is because you have to include these higher modes, because your physics at short range is three-dimensional. And even if you use a delta pseudo-potential, it remembers that it's three-dimensional, and you need to solve it exactly, taking into account all these higher modes. So for dipoles, I cannot give you an analytic solution, but what I can plot for a start is to try to extend this treatment from the previous slide and expand the dipolar potential in harmonic oscillator modes, but now using all of them. So I will have a multi-channel problem, and within each channel will be a different harmonic oscillator mode, and I will have couplings between the channels, which I can plot. This is the plot on the right, where here the dipoles are parallel to the trap axis to simplify the problem, because now the quantum number, the projection is conserved, so I don't have that many curves. And the potentials that you see are plotted in orange, and this approximation of a single mode is plotted in blue. So you immediately notice that due to coupling to higher modes, there is a repulsion, and this lowest adiabatic potential goes dramatically down. You can also plot adiabatic potentials using spherical harmonic basis, so more a 3D basis than the one-dimensional plotted here. For bosons or fermions, then you see this three-dimensional character because there is a centrifugal barrier for fermions at short range. But at long range, you again recover a harmonic oscillator spectrum. So this is the picture which gives you a nice intuition that there will be corrections due to higher modes, also for dipoles, and that they can be finite ranged, because here the axis here is the transverse length scale of the harmonic oscillator. So you can see that already at like half of this length scale, these potentials start to differ. So we approached the problem just with brute force and solved two particles with dipolar interactions in a harmonic trap numerically to see what we will get. And to mimic the physics of a Feshbach resonance, we change a short-range boundary condition. So we essentially impose a phase on the wave function at small separation. And here you have the spectrum as a function of this short-range phase. So one feature of this is that there are two branches corresponding to two bound states. One is dominated by S wave, and one is dominated by the D wave. And they are both coupled to the trap level. So these horizontal lines, if I plotted it using a denser grid, would be just harmonic oscillator trap states. And both of these states are coupled to this structure because of the dipolar interactions, which just do not conserve the angular momentum, which means that both S wave and D wave can couple. If I transform this plot, which is slightly unphysical because I have some short-range phase on the axis, to plotting versus the 3D scattering length, you also see that there are two branches which behave differently, and that the strength of the coupling between the bound and trap states is different. So I have wider and more narrow anti-crossings between these levels. So the message is already here. The physics is kind of non-universal. It will depend on the specific Feshbach resonance that you use and on this bound state that is causing you the resonance. So we can try to now map this 3D picture onto a 1D picture and try to fit an effective 1D potential which will reproduce this spectrum. And here we are trying to do that. And kind of surprisingly, we got the answer that for there are two parts, the effective short-range term with a coupling strength and something which would be your dipolar interaction. So we found that using this error function formula with a single mode kind of works for this spectrum. So you can reproduce all the features, but you pay the price that this G1D coefficient starts being strongly energy dependent. So here I label each branch with a symbol, and here I plot the G1D that I get from the fit as a function of the three-dimensional scattering length, and it depends on the branch. So there is a very strong finite energy effect, and in addition there is a shift of the position of the confinement-induced resonance as you go up and up in energy. So if you want to, for instance, do a topological pumping scheme where you go very high up in the energy spectrum, you will probably notice that there are corrections on the way. You can go to the optical lattice and solve something like two separate wells. And here you get an energy spectrum as a function of the separation between the two wells, which would mimic like two sides of an optical lattice with different tunneling strengths. What you see here is a trap-induced resonance, which also intersects with the trap states. So there is a bound state, which goes up and up in energy as you increase the separation. And then it crosses with the trap states, causing a lot of chaos. And here there are other branches causing more chaos in this spectrum, so it starts looking pretty funny. This is also applicable to tweezers, where you can really tune the distance between the tweezers in real time. And we think that these trap-induced resonances, they have been discussed by Deutsch, I think, more than 20 years ago, but they were very much ahead of their time. And now probably we can think of some nice metrological schemes involving this. Yes, if you want to use polar molecules, you will have many channels, so you'll have to further complicate the system. But the main conclusion is that you have to be careful with pseudopotentials, and the physics of real molecules in real lattices can be slightly different than what a theorist would love it to be. There will be non-universality and shifts of confinement-induced resonances, and it's because the system is essentially 3D, no matter how much you squeeze it. We think this can be used for some advantage, and if you're interested, the paper is here, and my group is here, and Michał is, where is Michał? I think here, yes, the guy with the hat. Thank you very much.
Thank you very much, Krzysztof. Are there any questions? Yes, Anna Maria.
Yes, so my question is, what about fermions? Is it possible, and how do you see a stronger dependence in space?
Yeah, we didn't yet try for fermions because the motivation was to do some quantum droplets, which Krzysztof Pawłowski was predicting with some simple models. So bosons were our first choice. But it's in principle is the same level of complication.
That could be interesting.
So just for me to understand, I mean, in the general scattering problem, there's of course, as the dipoles again get larger, always the question, can you still use Born approximation? Can you still separate into the two dipolar and contact interactions? I guess that was, I mean, you have done work on this yourself, right? So that was not included here, right? The fact that it now separates is really just looking at this one-dimensional problem, not taking into account any other complications that may still be arising in the 3D scattering.
Yeah, here the task is different. So I'm just trying to map a 3D model onto a 1D model on the level of potential. So I'm not talking about Born approximation here.
Good. Are there any more questions? Then let's thank Krzysztof and all the other speakers of this session again.